Hello. Just in case anybody's out there, let's see. Is my thing working? Do I have, yep, acceleration test review. I can take a look at this right now. There we go. Live chat is live. I can see it on my phone just in case anybody decides to. Hi, Brandon. Glad to see you here. Can you hear me? Can you hear me just fine? Yeah. Please respond if you can hear me. All right. So you see, I have some problems here. The ones in the one in bold are K problems, and I'll try to alternate back and forth between doing bold K problems and not bold L problems. But I have 3 K students in the thing right now, so let's go ahead and let's start with what we've got so far. Okay, so number 24. A jumbo jet needs to reach a speed of 360 kilometers per hour on the runway for takeoff. Assuming a constant acceleration and a runway 1.8 kilometers long, what minimum acceleration from rest is required? Okay, so let's start off by doing number 1, writing what we know. All right, it says the jet needs to reach a speed, so final velocity of 360 km per hour to take off from the runway. Assuming a constant acceleration and a runway 1.8 kilometers long, so that's our delta x, 1.8 km, what is the minimum acceleration from rest? Now it says right there from rest, so that means our initial velocity was 0. And step 2 now, write what we are looking for. And it asks, what acceleration do we need? Okay, so this one's going to be really pretty easy. Okay, so we're going to start off with our step 3, which is pick your EQ. Pick your equation. So if you guys remember this from class, VF squared equals VI squared plus 2AD. Now, as always, we have to check first to make sure that we know enough to use this equation. So VF is our final velocity. We have that given to us. VI squared, again, we have that given to us over here, plus 2AD. We don't know acceleration, but we do know delta x. So we have one unknown that leaves us with the enough to solve this equation. But let's go ahead and rearrange this before I start plugging in my numbers, okay? So if I subtract VI squared from both sides, I can rewrite this equation as VF squared minus VI squared equals 2AD. Now we're solving for that acceleration there, so we can divide both sides by 2D. Cancels out that guy right there. And what we are left with is a final version of our equation, VF squared minus VI squared divided by 2D equals acceleration. Now, those of you in my physics class might recognize this as the equation that you use to solve for the acceleration in our Marble lab, our Galileo lab this week. Okay, so step 4, plug and chug. Okay, so VF is 360 squared minus VI squared, which is 0, divided by 2 times 1.8 km equals our acceleration. Now let's go ahead and plug that in. Okay, so 360 squared divided by 2 divided by 1.8. Our acceleration for this, in order to take off with enough space, is 36,000 kilometers per hour squared. Now that sounds rather large, but don't forget, we're talking about whole kilometers over the space of whole hours. Okay, so it's nowhere near as much as it seems. Anyway, straightforward. I'm going to go ahead and just keep grabbing random questions until somebody out there asks me a question to address. So let's get rid of this guy and do something else. Vivian, Eileen, how y'all doing? Okay. So on the planet Vulcan, a ball is thrown upward at an initial velocity of 12 meters per second. Okay, so let's take a look right away. First thing you notice is one of those things that I've mentioned more than once. Unless we tell you something else, you can assume that you're on the planet Earth. But at the very beginning of this problem, it tells us that instead we are on the planet Vulcan. So that means that we're not going to have, or might not have, an acceleration due to gravity of 9.8 meters per second, and so on and so on. So some of our accelerations might be challenged. So let's continue to go. Okay. So what is the ball's velocity when it comes back down to the same height as it was thrown from? Okay. Now, writing what we know, on the planet Vulcan, a ball is thrown upward at an initial velocity of 12 meters per second. Uh-oh, messed that up. Okay, so for A, what is the, for letter A, what is the final velocity when it comes back down? VF down. Okay, we don't know that yet. B, if it takes 30 seconds, so delta t equals 30 seconds, for it to come back down to the ground, how long did it take to reach its highest point? So delta t down, so what is delta t1? And C, calculate the acceleration caused by gravity on planet Vulcan. So lastly, we need to do that. Okay, now again, if you remember from some of the problems that we did in class, this problem right here is a little simpler than it looks. Okay, so our VF down, whatever speed the ball hits the ground with, is going to be the same as the speed it left with. All right, now I'm going to show this in an example in a second, but you can see it. All right, so when you throw the ball up, it starts off fast. That's why I drew a longer arrow here and a shorter arrow and a shorter arrow, and eventually it stops. Once it gets up there, it starts coming back down slowly and faster and faster. Now, because of that, our VF down is going to be equal to our initial velocity, or 12 meters per second. Likewise, in order for that to be the case, it would have to accelerate for the exact same amount of time that it took to stop on the way up. So again, our delta t is going to be the same as our initial delta t. So 12 meters per second and 30 seconds. Now, I know that might not always look plausible, but let's go ahead and do an example where we assume that this is on Earth. Okay, so we have 12 meters per second. And then what we end up with is we're going to do an example where we think the acceleration is 9.8. But right now I'm just working on a separate thing. So our delta V is going to be equal to our A delta T, right? So it's going to start off at 12 and slow at a rate of 9.8 meters per second squared. So we have from 12 to 0, or a negative 12 meters per second for our delta V, equals negative 9.8 times whatever our time is. So 12 divided by 9.8, or 1.24. So our time in this example would be 1.224 seconds. Okay. Now, when we're trying to figure out how fast it's going to go on the way down, what we're going to do is we're going to figure out how high up it went. Okay, so delta x equals v0 delta t plus 1/2 a delta t squared. Now, just follow me along on this one. If you're willing to just accept that these are the right answers, then you don't necessarily have to keep following me. But I'm going to prove that this is the right answer. So we're solving for this delta x down here. Our original v was 12 times 1.224 plus 1/2 negative 9.8 times 1.224 squared. So if we punch all that in, I believe that's right. We end up with 7.346. Okay, we end up with that as meters. That's how high up it went. But so let's see how fast the object will go if we just drop it from that height, which would be the same thing as it slowing, stopping, and turning around and coming back. So if we have a, let's go ahead and use this one because we can. All right, so vf squared equals vi squared plus 2ad. When we just drop it from that height, vi is 0. So we're solving for this vf. Now 2 times negative 9.8. Actually, in this case, it's positive. Yeah. Oh, no, I was wrong because the d is negative. 7.346. Okay, so you see how I got this this number down here. This 7.346. That's how high up the ball goes if you throw it at 12 meters per second. Okay, let's see if I can get that. There we go. A little bit better. I'll figure it out on the next one. Tell me if I start running off the edge. All right, so we're going to go ahead and plug that in. So 7.346 times 9.8 times 2. Now, square root of the answer should give us our initial velocity. And for those of you paying attention, that is exactly what it gave us. VF equals 12 meters per second. So whether or not you throw it up and then it returns, or if you just drop it from this height, it ends up traveling at exactly 12 meters per second. And again, in order for it to accelerate to that speed, it would have had to be falling for the same amount of time. So there we go. Now we're done with our example. Let's actually solve this problem. Okay, so we've already got that the velocity of the ball as it hits the ground is 12 meters per second, regardless of what the starting acceleration is. And the time it takes to come back is 30 seconds as well. But now what we're going to do is we're going to solve this VF equals VI, VF squared equals VI squared plus 2AD to solve for that A. Okay? Actually, hold on a second. Oh, we actually don't need it. Sorry, my fault. Delta V equals A delta T. All right, so let's go ahead and use that one. It's going to be the simplest one. Now, we know that the ball stops at the top of its arc. At the apex, it slows down to a stop and then turns around and comes back. So our initial velocity for the coming down part is actually 0. Okay, and because of what we just talked about before, we know our V final is going to be 12 meters per second. It's given to us. Okay, we also know that our delta T to reach the ground is going to be 30 seconds again. Okay, so we know that our V final is 12. Delta V is V final minus V initial equals A delta T. Okay, and we know that our delta T is equal to 30. So 12 minus 0 equals whatever acceleration is multiplied by 30. Divide both sides by 30. And we end up with 12 divided by 30. So our acceleration is going to be equal to 0.4 meters per second squared. Boom. Any questions? Be quick. Okay, let me pick out a new one before we move on. Okay. Okay. I'm gonna do this. I'm gonna do this one if nobody responds. So no. All right. All right. Somebody come in with some questions. I'm just gonna keep doing problems until somebody stops me. I can see the. I can actually see the comments this time. So I promise I will at least try to respond. Okay. Okay, so again, this one's not in bold, so it's another L problem. On wet pavement, a car can be accelerated with a maximum acceleration of 0.2 g before the tire slips. Starting from rest, how fast is it moving after 2 seconds? All right, so 0.2 g, just like it says right here, 0.2 g means 9.8 times 0.2. All right, so let's go ahead and figure that out before we move on. Sure. All right, so 0.2 times 9.8. 0.2 times 9.8. That means the maximum acceleration of this car on this wet pavement is going to be 1.96 meters per second squared. Okay, so A, starting from rest, V0 equals 0. How fast is it moving after 2 seconds? Delta T equals 2 seconds. Our delta V is A delta T. So our change in velocity, Vf minus V0, is equal to 1.96 times 2. V0 is 0, so Vf equals 1.6 times 92, or what is that, 3.92? Yes, absolutely. 3.92 meters per second. So that's part A. Part B, how far has it moved? So delta x is what we're looking for. How far has it moved after 4 seconds? So we have another delta t, and that's 4 seconds. This equation is the proper one for this one. Delta x equals v0 delta t plus 1/2 a delta t squared. And again, we know everything in this equation except for delta x. We know v0, that's 0. We know delta t, which is 4 seconds. We know acceleration, which is what we calculated up here, that 1.96. And our delta t squared is, again, 4 squared. So 0 times anything is 0 plus 1/2, 1.96, 4 squared. So 1.96 times 16 divided by 2. 15.68 meters. Okay. Now I can imagine that this kind of problem with words like wet pavement and slipping and 0.2 g can be kind of confusing and maybe even a little intimidating. But in the information in the problem, it even tells you how to calculate acceleration using g. So deep breath. And everybody say it with me. Physics is easy. We need to say physics is easy. If you tell yourself that you can do it, you're much more likely to be able to do it. All right. Moving on. I have a request for a K problem. Excellent. Thank you, Adam. Physics is easy. All right. Okay. There we go. A record of travel along a straight path is as follows. Start from rest, v0 equals 0, with a constant acceleration of 2.77 meters per second for 15 seconds. Constant velocity for the next 2.5 minutes. Everybody see that? We've been talking about seconds, but this one gave us minutes. So then constant v for delta t of constant v for 2.05 minutes. Let's go ahead and convert that right away. So we need minutes down here on the bottom. For every 1 minute, there are 60 seconds. So 2.05 minutes times 60 seconds is 123 seconds. Next, constant negative acceleration for, actually, you know what? Let me go ahead and start this over. It's okay to start over, guys. I'm going to draw this out a little more easily. I know I'm going to want a picture. Okay. So this is a VVT, time and velocity on this side. All right. So start from rest. So starting from 0. And we're going to split this into 3 sections. Okay, I'm going to do my best. So A, B, and C. Let's go ahead and write our stuff down in that order. Okay, so A is start from rest, constant acceleration for 15 seconds. Everybody can see everything? Good, good. B, so whatever VF is in this section is going to be our initial velocity in this section, okay? And our time, like we already calculated, is 123 seconds. Just in case you're just joining me, that is 2.05 minutes converted into seconds, okay? Then in C, again, our initial velocity over C is going to be the same as whatever the final velocity is in part B, okay? And then constant negative acceleration of negative 9.47 meters per second for a delta t of 4.39 seconds. Okay. Now, we're not 100% sure what, if any, final velocity we have here because it doesn't say that we come to a stop. It says that we slow at 9.47 meters per second for 4.39 seconds. Okay, so we're going to need to figure this out a little bit. So first things first. In section A, we start at 0. We accelerate at some constant, or at a constant of 2.77 meters per second, and this total time period is 15 seconds. Okay, we know that we hold this for this long, which we already calculated is 123 more seconds. So this section right here is 123 seconds. So 15 plus 123 is 138. And then we slow to some speed for another 4.39 seconds, or a total of 142.39 seconds. Okay, so our total time is right there. That's our delta t total. That's going to be necessary for over here where it says what's the average speed for each leg in the total trip. Okay, so starting with letter A, we need to calculate just how fast we end up going. I can already tell that's what we're going to need to do. Okay, so delta v is equal to our acceleration multiplied by our time. We have a time, we have an acceleration, so we can do that. So v2 minus v1 equals our acceleration, which is 2.77 times 15 seconds. our initial velocity is 0, so that goes away. So our final velocity is 2.77 times 15, or 41.55 meters per second. That's our final velocity, and let's go ahead and add that to our graph. 41.55. So 41.55. Now we know that we're traveling at that rate through this section as well. 41.55, 41.55. Excellent. And we know that we're traveling for 123 seconds. Okay. Next, we know that our initial velocity for part C right here is also that 41.55. See, this is why it's important to make sure your arithmetic is really good from the very beginning, because if I mess this up right here, 2.77 times 15, if I mess that up, it means that all of the rest of my stuff is going to be at least a little wrong. Okay, and now let's figure out what our final velocity is here in section C. Something tells me it's probably 0, but our delta V for C, let me put that A over there. For C is, again, A delta T. Now, V2 minus V1 equals negative 9.47 times 4.39. Our initial V over here is now 41.55. And let's see what 9.47 times 4.39 is shockingly negative 41.55. It's actually 41.5733, but it's 0. And let's go ahead and make sure that we write that out. So if we add 4.1 to both sides, all right. So let's go ahead and write that explicitly so that anyone who looks at it from now on, including a teacher grading your work, will know that you have said that there. Just in case I was, in fact, looking for that 0.0233, this would tell me that you had interpreted that as 0, and we're moving on from there. Now, we're supposed to calculate the total displacement for the entire trip and what the average speed for each leg of the trip was, and for the entire trip. So we're going to calculate displacement in chunks and our average speeds over that period of time, because we have our times, our average speed or average velocity is just our delta x over delta time. Bringing back a classic. Okay, so this guy right here, this delta x for part A, is going to be the area of this triangle. So 1/2 base times height, or 1/2 base is 15 seconds, and our height is our change in velocity, or 41.55. So let's go ahead and calculate that. I'm running off the edge of the board again. Okay, there we go. So 15 times 41.55 divided by 2. Okay, so initial part A, our delta x is 311.625 meters. Okay, and now that we have our delta x, we can calculate our average velocity for that period. So we take so this is our displacement for that section. Our average velocity, sorry, it's getting all bunched up. It's a long problem. Is delta x over delta t, or 311.625 divided by 15, or an average of, okay, I'm just going to erase a chunk of this. So let me clear some space. Our delta x for part A is 311.625, and our V average is 311.625 divided by 15, or 2.7 55.75 meters per second. Okay, that's for part A. Let's clear some more space. Okay, now for this part right here, it's a rectangle. So our delta x is going to be the area of that rectangle, or length times width. For this one, our width is 123 seconds, and our height is, again, our velocity over here. So it's 41.55. And our total distance over that period is 511.0.65 meters. Okay, that's for part B. Part A. Now, you probably can tell right away what the average velocity is over that period, because the velocity doesn't change through this time period. So our average velocity is just going to be that 41.55. But let's go ahead and do it anyway. So our delta x is 123 times 41.55 divided by our time, which is 123, or our average velocity is at 41.55 meters per second. And I didn't even have to punch any stuff into my calculator again. Okay. Somebody asked me a question. If nobody asks me a question, my next problem will be my last one. Okay, for part C here, again, you can tell this is a triangle. So our delta x is going to be 1/2 the base of that triangle, which is 4.3, times the height of that triangle, which is our velocity, 41.55. So 0.5 times 4.39 times 41.55. Or 91.20225 meters. Okay. And for the sake of consistency, we're going to calculate our delta v, or our average velocity there, which is going to be our delta x, 91.20225 divided by the time period, there we go, or again 20.775. Now I don't want to add just another, oh, that's not the kind of question, Angelina. Ask me a specific question. Mr. Blades, I'm having trouble with this particular thing. Could you please solve this particular thing? Then I will do that. All right. So if you're paying some attention, I don't want to add too many wrinkles to you, but these two right here, this 20.775 and this 20.775 is just half of the initial velocity, or half of this velocity up here, 41.55. Okay, because again, if we wrote this out divided by 4.39, all we would have been left with is 1/2 41.55. And it makes sense because you start at 0, go straight up to a certain thing. The area carved out by that triangle is half of this rectangle. So your average velocity is going to be half between the 0 and the top velocity. Okay, but so let's go ahead and do the last little bit. We already got our average, we got our distances and our average velocities for each chunk. So let's go ahead and solve our delta x total and our v average for the whole thing. Okay, so our delta x total is going to be 311.625 plus 511.0.65 plus 91.20225. So let's punch that in. So 5513.477 meters. That's our total displacement over that period. Okay, and then our average velocity is delta x over our total delta t. We already solved for our total delta t over here, so 5513.477 divided by 142.39 seconds. So, or our average velocity, let's go ahead and write it nice and big, is 38.721 meters per second. Okay, now let's discuss that result. It seems really high because we start at 0, we end at 0, and this 38.721 is really close to our 4155 over here. Now, does that answer make sense before we start moving on? Now, I submit that it does, okay? Because even though I'm drawing this way, it's really not to scale. We're in part B, we're in section B for almost 10 times as much time here and over 30 times, almost 30 times as much time there. So our average is going to be much closer to the average velocity spent in time B than anything else. So I maintain that this is a perfectly logical and possible solution, and I see no reason to keep working on it. All right, moving on. We'll do one more, or I can answer, specific questions should anybody have one. And for the record, all of these are test-like. All of these are very similar to what you might see on a test. Okay. Let's see. Is there a concept anybody out there is having trouble with that I could address rather quickly? Because if not, like I said, I'm going to head out after this next problem. Nope, we already did that one. Nope, that one's too easy. Actually, you know what? It sounds complicated, so let's go ahead and do it. Okay, a muon, an elementary particle, is shot with a constant speed of that into a region where an electric field produces an acceleration of the muon of 1.25 times 10 to the 14th meters per second, directed opposite to the initial velocity. How far does the muon travel before coming to rest? Okay. Now, this has a lot of weird language in it that doesn't actually mean much. So let's go ahead and decipher to start with. A muon, who cares, is shot at a constant speed. There we go. There's some words that we need to know. Yeah, don't worry about the muon one because, like I said, most of it is nonsense. Okay. Into a region where an electric field, again, don't care, produces an acceleration, there we go, of the muon directed opposite to the initial velocity. So that means our acceleration is going to be negative. Times 10 to the 14th. How far does the muon travel before coming to rest? Okay, so first of all, let's compare these. Now, these numbers are very, very large, okay? Again, negative doesn't mean small, and as you can tell, these numbers are very, very large. Okay, there we go. Can you see me? Can you see me? Ah, here we go. Now I can see better. See the whole thing. Excellent. Okay. So this is 5.0 times 10 to the 6th. This one is 1.25 times 10 to the 14th. Now, for those of you who haven't gotten to scientific notation yet, that means that this one is roughly 1, 2, 3, 4, 5, 6, 7. Or 10 million times larger than that number. So even though this is pretty quick, the answers we're going to expect are going to be pretty small. Okay, so let's move on. We know that the muon ends up at rest, so our final velocity is 0. Okay, so even though there was a lot of flowery language and it seemed very strange, we now have two velocities, an acceleration, and we're searching for a time and a distance. This is a problem that we know how to do, even though a muon, which is super cool, and I'm more than happy to talk to you guys about, has absolutely no importance to us doing this problem. Okay, so our delta B is equal to our VF minus our V initial, but also to acceleration multiplied by time. Okay, now we don't have to start here, but I want to, and then I'll do it in a couple different ways so that we can see how it's applied. Okay, so VF minus VI equals whatever. So 0, because that's our VF, minus 5.00 times 10 to the 6 equals our acceleration, which is negative 1.25 times 10 to the 14th multiplied by our time. Now, if we divide both sides by 1.25 times 10 to the 14th, yeah, my handwriting's terrible. Again, we can see our time is going to be very, very short. So 5 e times 10 to the 6th divided by 1.4, oh, nope, 1.25 e to the 14. So again, our time is 4 times 10 to the 8, times 10 to the negative 8. So roughly 1/10,000,000th of a second. Okay, so our time is 4 times 10 to the negative 8 seconds. Okay, so again, we're getting some of the things we expect. Now our delta x is v0 times our time plus 1/2 acceleration delta t squared. Okay, so this one's pretty easy to write. 5.0 times 10 to the 6 times 4.0 times 10 to the negative 8 plus 1/2 negative 1.25 times 10 to the 14 times 4 squared. Okay, now this is one of those ones that you need to be very careful when plugging stuff into your calculators. Okay, I don't anticipate that we'll give you any with this kind of thing on them, but I do have graphing calculators should we need them. Okay, so 5.0 times 10 to the 6th times 4. There we go. So our 5.0 times 10 to the 6th times 4.0 times 10 to the 8th is equal to 0.2. Let me make sure that that's right. That doesn't feel right. Yeah, that's what it is. 0.2 plus negative 1.25 e to the 14 times 4e to the negative 8 times 4e to the negative 8 equals negative 0.2, or times 0.5 minus 1. So our total delta x from our problem is 0.1 meters. Wrote it wrong. Meters. Got to be meters. Okay, so let's go ahead and check this against another way of doing this problem to make sure that we in fact got our right answer. If everybody followed that, just stay silent. If you had any problems with what I just did, send chat me some message so that I know. So we use this. Now let's go ahead and use a slightly different one. Okay, so VF squared equals VI squared plus 2AD. We know VF because it's 0. We know VI because it's given to us. We know 2 because it's 2. We know acceleration because, again, it's given to us. Now all we have to do is solve for D. So if we subtract VI squared from both sides and divide both sides by 2A, we have negative VI squared equals 2A equals D. Okay, number 4, plug and chug. So negative VI squared is 5.0 times 10 to the 6th squared negative divided by negative 1.25 times 10 to the 14 times 2. Let's go ahead and plug that in. 5e to the 6 squared divided by 1.25 e to the 14 divided by 2. And surprise, surprise, I'm not surprised at all. 1. Boom, there we go. You can see that we got the same answer in both spots, that it worked out quite well. Okay, that is one of the more difficult ones, and you can see that all the rest of our problems are quite similar. So let's take a look. A bus traveling at 30 km/h accelerates at a constant 3.5 meters per second for 6.8 seconds. What's the final velocity in kilometers per hour? Now, I'm not going to bother to do this one because nobody's been asking me any questions, but let's walk over it a little bit before I sign off. We see a velocity in 30 kilometers per hour, but we're given an acceleration in meters per second per second. We know we're going to have to convert. We're going to have to convert that meters per second into kilometers per hour. And this 6.8 seconds into a fraction of an hour. But after that, it's really easy. Delta V equals A delta T. So, all right. We've covered the vast majority of the types of problems that we could give you. But let me just talk generically towards the end about the different kinds of equations we've got. Okay. So we have delta V equals A delta T. All right. I usually like to write it that way because it's nice and flat. But remember that this one is also organized as delta T equals delta V over A, and A equals delta V over T. Okay. Now, what each one of these ones means. Now, delta V can also be written as V2 minus V1. Okay. So using a bit of substitution, you can solve for almost anything. But let's take a look briefly at this one. This is our identity here. Delta V over T is how we define acceleration. And now if we have a VVT with velocity in meters per second, time in seconds, we have some graph there. Now, if we were to solve for the slope of this line, we would find that y is some change in the velocity, or delta V, and x would be some change in time. So what we have here is the slope of this line on a velocity versus time graph is our acceleration. We've defined it that way, and that is important to remember. Next, our delta x equation. Okay, now this one has complicated roots. Okay, could you still get the same answer if you don't rearrange the equation? Okay, here's the important thing. This equals that equals that. All of these different forms of the equation are the same. All right, so if I have 4 chairs in my room, let's say my 4 chairs are my delta V, my A, my time, and delta X. If instead tomorrow you show up and my chairs are arranged this way, there's still the same number of chairs there. They're just organized a little differently, but they are the same chairs and they're still there. All right, so all of these different versions of the equation are in fact exactly the same. They're not even basically the same. They are exactly the same, and you will get the same answer. But sometimes I like to do 2 different ways just to make sure that I got the right answer. And if you look at the last problem we did, we used 2 totally different approaches and ended up with the same answer. So definitely, if you use different forms of the same equation, you're going to get the same answer. So let's go ahead. Delta x equals V0 delta t plus 1/2 AT squared. Now, we talked about using a little bit of substitution, but don't forget, if we use this A equals delta V over t and substitute it into here where A is, we can get this version of the equation. Okay, now the reason this is useful sometimes is if we're given 2 different velocities, a V initial and a V final, we can either use it and calculate this acceleration here, or if we don't feel like having to solve an equation with a square in it, we can then use this version of the equation. But likewise, if we're given an acceleration and not told what the final velocity is, we don't even need to find out what it is in order to use this equation. Okay, so just by playing around with these math equations a little bit, we can see that we can use a variety of different things to cut ourselves some slack. And then lastly, this equation right here. Now this one's a little strange, and again, for those of you worried about it, if you combine this one and solve, you actually end up with this. Okay, because you see our delta x there, there's our delta x, our a is right there. If we do some substitution, we actually end up with this exact thing. All right, so don't worry about it. But when would I use this equation? Okay, I would use this equation when I'm told that something either comes to rest or starts from rest or stops or a red light or something. I would use it there. And if you can tell, something that is very prominently featured in a lot of these other equations but is not shown in this equation is time. Okay, if you're given some velocities and maybe even a distance or an acceleration, but not given a time or how long you're moving, I would encourage you to start by trying to play around with this equation. And again, you can only solve an equation if you have one unknown. I've had some students, for some reason, if they have more than one unknown, they just substitute in the number 0. That's not how it works. Okay, so I've been on a little over 50 minutes. It is time for me to go. I'm confident in all of you. Take a deep breath. You've studied hard. You've been with us for a whole hour on this thing. I've done the hardest problems that I could find. And if you got through that, you're pretty well fixed. Okay? So thank you guys.